Okay, thank you very much to all of you that were implicated in the organization. I wish to be in Perugia, but this was the time. So I will present you, let's say, a classical idea in geomorphometry in GIS, pixels versus objects applied for burial mound detection. Using geomorphometry and statistical methods. So the idea came to me after publishing an object-based method for burial mound detection on high-resolution data. And after I saw a paper from Guyot and his team from 2019, which applied something similar in a pixel-based approach. So I adapted my method to the pixel-based approach for the same study area where I was performing the object-based approach. In Romania, the burial mounds are of kurgan type. You can see on my background how a kurgan burial mound looks like. So they are mainly smoothed because they are quite old compared with other types of burial mounds, or tumuli, how they are called in the literature. These kurgan type burial mounds, they appear from Yenisei River to the middle Danube River, and they were constructed between the Neolithic period to the Iron Age, with a very dense period during the Bronze Age by different cultures. These are the two study areas. One was used for the training of the method and one for the testing of the method or for the validation. The one on the left for training and the one on the right for validation. They are neighboring areas. The left one is to the north of the right one. You can see hilly areas with quite wide floodplains, and we have burial mounds appearing all over the landscape, on the ridges, on small plateaus, on hill slopes, but also over the floodplain. So the first step was to delineate the burial mounds and also other type of mounds that were found on the high resolution DEM, which is based on LiDAR data. We used 5-meter DEMs, which were, of course, resampled from 0.5 DEMs because of the burial mound geomorphometry. You will see because of their size. It can clearly be seen that we have burial mounds on all over the landscape. We've had for the training 98 and for the validation 32 mounds, from which we have 69 burial mounds and 29 burial mounds respectively. Here you have some pictures. They were checked in the field to validate the fact that we have a burial mound and we have not other type of mound, which can be an electric pole base or deponia or something similar. Here you have the geomorphometry of the burial mounds. Basically, we wanted to see if these burial mounds have, let's say, a geomorphometric signature. We have the training set, we have the validation set, and we have the other types of mounds, not burial mounds or not kurgans. And it can be clearly seen that there is a certain signature if you look at the area, the height, or even shape index or local convexity or maximum curvature. Also, we tested a wide range of geomorphometrical variables to see if there are indeed differences between the burial mounds areas and non-burial mounds areas in order to see if it is fitted to derive a methodology to delineate them. We did this in an object-based approach. We basically used segmentation, watershed segmentation of local convexity. We also used a well-known geomorphometrical method to derive peaks, basically in 3x3 windows. And then we used the seeds of the watershed segmentation with the focal peak to select only those segments that could potentially be burial mounds. And then we used various geomorphometrical parameters of those segments in a statistical algorithm, which is random forest, in order to derive the final product, which is showing us the burial mounds data. You have here a snapshot of the method. You can see the peaks with green and the selected peaks with red. The selected peaks are basically peaks that correspond to watershed segmentation seed, which is in the local neighborhood. In this way, we basically were able to eliminate small features which are presented especially on ridges, but also on floodplains that could represent just small roughness topography of these areas. We tested the index of convergence and also the convexity as measures for delineated the burial mound segments. We have through manual inspection seen that actually convexity, local convexity, is the best approach in this way. Local convexity, which was introduced in the literature by Iwahashi and Kamiya in 1995, actually computes the percentage of convex upward cells within a certain radius of pixels. And this parameter is ideal for the case of burial mounds in terms of identifying the whole convexity of the burial mound beside the peak, which can be selected using simple filters. Here you see the entire workflow, starting from deriving peaks, deriving local convexity segments, selecting from the peaks only those segments that have also a seed in the surrounding of the peak, and then computing all the geomorphometrical variables, statistics for that segment, and then using random forest to select from those segments which have a selected peak only those that might represent burial mounds. And here you have the result, which is quite good, is the confusion matrix for the external validation area. You can see that from 27 burial mounds, the method is finding 25. And we also have 42 false positives, which in general are very close to the true positives. So it's very easy to browse to them and to select the true positives. We used a lot of geomorphometrical variables and tested their usage, and then we stopped to only shape variables and the descriptive statistics of altitude and index of convergence for fitting the random forest model. This was made in the tuning approach. So basically we have chosen the best possibility from the entire set of over 100 geomorphometric variables and their statistics. Okay, so usually random forest is seen as a black box by someone, but actually, if you take a look at the methodology and use the graphs that can be used to see inside these trees, actually you can derive very good conclusions about the method and why we were able to obtain this very good result. So basically we have trees which start from a root and then multiple sub-trees based on certain decision until we reach a leaf node where the this decision stops, and we have the classification burial mound or non-burial mound. If we look at the diagnostic plots, we will see that basically Not always the statistics measures that are used by the methodology actually are okay. Basically, we have to look at the confusion matrix. In general, machine learning techniques need a lot of variables. So from a certain point of variables on, basically you will get quite stable results. And also, we perform tuning to see the node size and the M-try parameters to find the best ones. So you can see here the plot of the first 20 variables that were used to create the trees and to stop them. You can see that they are quite deep trees until 28 level. And we can see that the standard deviation of altitude, the 90 quartile of index of convergence, the range of altitude, and so on, give or represents geomorphometric variables that are used basically to find the burial mounds. Also, there are a lot of plots there that are showing us how these variables are used. Some words about the index of convergence, which is basically computed in regard to overland flow and can be quite easily used to identify local peaks or also local pits. Also here, the interaction inside the trees. And also the idea is that basically the object-based approach is able to identify very well the statistical space of the burial mounds compared to non-burial mound segments. So this was the main power of the method. Basically, we also obtained the delineation of the burial mounds beside their location, which is quite good. You can see on this histogram that many of them, they are quite well defined, delineated. Then what about the pixel approach? The pixel approach was implemented on pixels with quite the same philosophy of the random forest model. Normally, we would say that the numbers are better, but actually the big problems, which is to look at the results, as the special results, is the fact that we have too many false positives. So basically here you have the segment that was selected as a burial mound, and here you can see a lot of false positives, which basically will make very hard to identify the real burial mounds on such an approach. So here we have the diagnostic plots for the pixel-based approach, which shows us mainly that the statistical domain is not very well covered. This is the main problem of the method. That's why we get a lot of false positives. You can see it's very hard to establish the statistical feature space. So in our view, basically the object-based approach is better because it's able to define very well the feature space. Attention is needed to the confusion matrix accuracy, which can be misleading. Big numbers of false positive basically can create a lot of problems. So in our view, the geomorphometric expert opinion is needed when such landform classification is targeted, and the machine learning algorithms are very good in doing the job, but you have to choose the right variables. Thank you very much.